Yuejie had to go.
Yeah.
She'll probably come back. I don't know. She told me to. She told me she will not be here. Okay, let's start. Okay, everyone, thanks for coming back after the lunch. So there's still some people outside, but I think I'll get started with announcing. So we are fortunate to have Professor Yuejie, who's like the Yale Statistics and Data Science Department. This is surprising, the first time we are both meeting each other. But yeah, she's done some really great work in federated reinforcement learning, and I'm excited to hear more about it.
Thank you so much for the introduction, and it's a great pleasure to be here. I feel almost guilty to be here, considering there's a big snow blizzard right now happening at Yale, but still very happy to be here. So this is actually, I'm going to talk about federated reinforcement learning, basically how to do reinforcement learning in a federated setting, particularly focusing on the Q-learning algorithm. This is actually based on a few papers jointly with my wonderful colleagues at CMU, where I just moved from last year. So Jean is a student co-advised by me and Gauri is just sitting right there. And Sudeep was my former postdoc who just joined Meta recently. All right, so let me get started. So I'll start maybe with a very brief introduction of reinforcement learning. This is sort of the machine learning paradigm that's, I think, different from a few of the talks we've seen previously this morning, where essentially consider sort of this interactive learning where the agent tries to learn sort of how to take their best actions in an unknown environment through trial and error. And perhaps the first time a lot of us starts to really feel the sort of the power behind reinforcement learning techniques is when we have the AlphaGo paper comes out. And it's a little bit hard to believe this is like about 10 years old now. And since then, we start to see a lot of small successes of reinforcement learning across different various fields, from in robotics, resource management, in wireless systems, communication systems, chip designs, controlling nuclear plant, and many, many other applications. And last but not least, I should probably also say that reinforcement learning is having a strike back that is being used for doing post-training, right? And getting us a lot of this kind of very nice thinking models, thinking machines. So it's probably not an exaggeration to think RL really holds a lot of promise in accelerating scientific, engineering, societal advances. But the question is, how do we do this in a more efficient way? So in my talk, I primarily care about two things. The first thing is the sample efficiency. So a lot of the successes we've seen for reinforcement learning really happens when you have nice simulators where you almost have unlimited resources to generate many, many samples or rollouts that you don't really care about the cost per sample per se. But in a lot of other more real-world engineering applications, getting a lot of data samples are actually very, very costly. So how do we design more sample-efficient RL algorithms, right? The other aspect, well, given that, I think one thing we will be looking at today as a theme of the workshop is to think about how to leverage federated learning in this kind of setup. Right? So the kind of picture we have, I will later show, is that if you have a lot of maybe workers, agents that can collaboratively help you to train the policy, is it possible to harvest the power of federated learning to get more efficient, more runtime efficient reinforcement learning algorithms? So this is sort of the high-level question. And sort of the mental picture we've been trying to inject in your mind throughout the talk is some sort of paradigm like this. So this is more like the where you have a parameter server, but a lot of the things we talk about can also be extended, generalized to a more decentralized setting where you have only these agents talk over a decentralized topology, for example. But roughly speaking, we'll imagine there is a central server that helps you to coordinate the information sharing across the different agents. And the agents will be trying to do basically what they are supposed to do in a reinforcement learning task. So the idea is that we would like to be able to leverage the existence of multiple agents. And hopefully they can learn collaboratively sort of getting you to the global optimal policy in a faster fashion. Okay, so that's the high-level task. Of course, as we are doing things in this federated setting, there will be inherently new trade-offs coming along. So intuitively speaking, if you are allowed to just share everything with the server, then clearly you will be able to sort of cut the number of samples you need per agent, basically by the number of agents you have, right? So that's the so-called linear speedup that we often hear a lot in the federated learning setting. But by doing that, you will cost a lot on the communication end, right? On the other end, if you don't do communication at all, you just have every agent sort of work in their silo, so you're not going to get any collaboration gain, but you are also not going to cost you anything in terms of communication. So naturally, there will be some kind of statistical communication trade-off. So the kind of question we want to answer is, one, is linear speedup possible when you have just a reasonable minimum amount of communication given? And if there is a communication bottleneck, is there a price you need to pay in terms of the communication cost? So that's sort of the running questions we would like to be able to answer. So with that in mind, the talk will be roughly divided into 3 parts. So in the first part, we'll be just to sort of answer the first order basic question, whether we can achieve linear speedup. The second question will be more on the communication side. So particularly, is there a minimum premium you need to pay in terms of communications cost when you run this kind of federated learning paradigm in the sort of distributed context, particularly for long horizon type of problems? Finally, the last question is about heterogeneity, where maybe all these agents are heterogeneous. And in that sense, in that case, how do we best sort of collaborate among them? How do we design better maybe information fusion strategies to maximize the gain of collaborative learning? So that's sort of the high-level agenda for today. So as I get started, let me first introduce the basic model and the basic algorithm we are going to look at in this talk. So we'll be using Markov decision process as our running model for studying reinforcement learning. And we'll be looking at this one algorithm called Q-learning. But again, a lot of the things I talk about today, I think you can sort of very easily think about how to extend them and generalize them to other RL settings and other type of RL algorithms. All right. So for those who are very familiar with MDP, so bear with me, but just make sure everyone is on the same page. So MDP is sort of this kind of closed loop paradigm where it tells you how an agent interacts with some environment. We're going to model the environment using some state space S. In this talk, we're going to assume these state space are going to be finite, but potentially very large. So every element in the state space tells you a possible configuration of the environment. The agents will be interacting with the environment by making actions from the action space. So again, in this talk, we'll be assuming the action space is a finite set, but potentially very large. And upon seeing an action from the agent, the environment will push a reward to the agent, which is a function of the current state and the current action. So without loss of generality, we'll be assuming the reward are normalized to 0 and 1. What the agent wants to do is to design this so-called policy. That is, given any possible configuration of the environment, the policy tells what kind of actions the agent should be making by drawing from the policy that's defined as a probability distribution over the action space. Okay. I hope this is clear. And finally, the most important bit is that environment is changing over time, so that after one round of interaction, the environment will move to the next state that is specified by drawing a sample from the transition kernel. That is basically a probability distribution over the state space given the current state and the current action. Okay. So the goal of reinforcement learning, or MDP, is trying to learn the action. By doing that, we need to first know how to measure the goodness of a policy, and that comes to the notion of these value functions. So the way these value functions are defined is that assuming you are given some maybe initial configuration of the environment, say S0, and then the agent will be just rolling out a sequence of actions according to the policy pi, and along the way, it will be collecting a sequence of rewards. So the value function of the policy in this kind of infinite horizon discounted setting is that it's simply going to look at the expected discounted total sum of the rewards you collect along the trajectory, where future rewards is going to be discounted by factors of gamma. Okay. Now, similarly, another very important quantity is that these Q functions. It's defined very similarly as a value function with one important distinction, that instead of just fixing the initial state, you're also going to fix the initial action and then roll out the rest of the actions according to the policy pi. So by doing this, your Q function is a two-dimensional table, right, over both the state space and the action space. Importantly, gamma is a discount factor. So this has a lot of mathematical reasons behind it that I will not get too much into, but as you can see, by having the discount factor strictly smaller than 1, you essentially ensure this sequences always converge. And roughly speaking, if you do some geometric sum argument, you get this nice number 1 over 1 minus gamma. Remember, the reward are all normalized to 1, right? So this number essentially tells you, in effect, how long of a horizon you care about for your problem. And this is a very important quantity in reinforcement learning, that it will just shows up in a lot of the complexity analysis. So if you care about long horizon planning, then gamma will be set very close to 1, and the effective horizon will be a very large number. Potentially can be thought as even comparable maybe to the dimension of state space or action space. So you will start to care about its scaling, for example. Okay, so this is sort of the basic RL problem. Now with this in place, essentially what we care about is to find the optimal policies that maximizes its value functions. So if we know the exact configuration of the environment, then this just falls back to the classical paradigm of dynamic programming, where we know all the nice solutions are given by the Bellman's optimality equations. But in RL, you actually want to learn the optimal policies through using stochastic samples drawn from the MDP. And a little bit on the notation side, in the talk, we'll be talking about all the optimal quantities by putting a star on top. So Q star, V star, pi star as the optimal value functions and the policies, so on. Okay, so that's sort of the basic model. Then how do we learn the policy using the samples? We're going to actually look at this classical algorithm Q-learning, originally proposed by Watkins and Diane. This is actually a quite straightforward algorithm which is basically applying stochastic approximation to solving this kind of Bellman's optimality equation. So the optimal Q function is actually the fixed point of the the Bellman optimality equation shown on the bottom. Okay. But in this population version, you have all this. You have to have access to the exact knowledge of the transition kernel, which is not available in the reinforcement learning setting. Rather, we are going to assume, as a first case study, we have samples from a generative model. So this is actually probably the most simple model you want to look at. This is just assuming that at every iteration, I'm going to assume for every state action pair, I can observe a transition from it. So the transition, I have this generative model that will output the next possible state to me called S prime. And I have this for every state action pair. And if you have this kind of synchronous model, then the way the Q-learning algorithm works is actually very straightforward. Basically, at every iteration, you're going to update your Q value estimate by taking a convex combination of the previous Q function estimate and sort of a sampled version of the Bellman operator, where instead of using the population Bellman operator, you simply replace the next state as prime by the one you actually observed. So I don't know if you can see it clearly, but on the bottom, essentially, the only difference between the stochastic version and the population version is essentially it drops this expectation, right? But just using the sample you see. All right, so very simple Q-learning algorithm. But surprisingly, there has been a lot of analysis for sort of the sample complexity of this algorithm. And we have been sort of get a sharp sample complexity until very recently. So the question we care about, assume you want to learn the optimal Q function in an entry-wise manner up to some epsilon accuracy. How many samples does it need? And we have this sort of sharp understanding, essentially, that tells you that the sample complexity scales at this number. So it will scale as the size of your state action space times the false order of the effective horizon divided by epsilon squared, where epsilon is our accuracy. And this is, in fact, sharp. So let me explain this a little and why this is interesting. So first of all, for people who know about this problem, so we actually know the minimax lower bound for this problem is actually has a dependency with the effective horizon on the third order rather than the fourth order. So and this is achievable by using a model-based approach. So what this is showing is also sort of a sharp divide from the model-based minimax lower bound, what a minimax lower bound that is achievable by a model-based approach versus what is achievable by a model-free approach like Q-learning. And this is actually, as I said, sharp for Q-learning, which means you can actually find instances of MDP where when you run Q-learning on top of it, the sample complexity actually scales provably on the fourth order with the effective horizon. So this basically gives you a sort of a tightened understanding of the sample complexity of Q-learning. With this in place, again, the point of this talk is not to talk about single agent setting, but sort of set up the stage of what we can achieve in the single agent setting. And then later this helps us to benchmark the performance we'll obtain in the federated setting. All right, so with that in place, let's now get into sort of the meat of the talk, where we want to look at the federated version of this Q-learning algorithm. So let's start with maybe the most natural variant of Q-learning in this kind of federated setting. And this is actually very similar to the way you may want to run, say, the local SGD. Right? So the idea being, I will have a bunch of these agents, and each of the agents will have their own simulators in place. Locally, they're just going to run this kind of local Q-learning update for a number of local rounds. Let's say they run this asynchronous version for tau rounds. And after that, they will do one periodic averaging, where they simply average all the local Q functions and get an averaged Q function. And the server will send back this averaged Q function to the agents. And the agent just goes back to the local updates and so on. Right? So very intuitive and very similar to what you would imagine maybe from a federated learning perspective. Okay. All right, so the question is, can we actually achieve faster convergence, right? Things like linear speed up in this kind of very natural setup. So the answer turns out to be yes. So we have actually earlier papers that look at this. Essentially, we show that to achieve, say, still the epsilon accuracy, the sample complexity essentially scale as, again, as A divided by K times 1 minus gamma to the fifth order times epsilon squared. Assuming you choose, say, the communication period properly and the learning rate properly. So importantly, K here is the number of agents you have. So effectively, this allows you to get a linear speed up when you benchmark with the best achievable sample complexity in the single agent setting. So we are only suboptimal by a factor of the effective horizon. And this may be closed by, for example, doing a more refined analysis. You can actually also show the communication complexity can be made essentially independent with the accuracy. So if you care about solving this to high accuracy regimes, then the communication complexity essentially becomes amortized over time. Recently, we have been also looking at generalizing this kind of analysis to the average reward MDP, where you can actually show similar type of linear speedup. All right, so if you put this in a picture to compare with some of the prior art and also sort of the best result we have in the single agent setting, you see that this is basically allows you to get a first order approval for this strategy, right? We can get indeed linear speedup with a near optimal parameter dependencies with all the salient parameters like state action space, discounted effective horizon, things like that. All right, so that's nice, but let's maybe try to go a little bit beyond this basic setting. So the next question I want to look at is more on the communication side. Because we see that, yes, we can get this kind of linear speedup with reasonable communication cost, but it's really not clear sort of the optimality of the communication cost in this kind of settings. It's good to get sort of into understanding on the sample complexity side because we are able to benchmark with a single agent result. But we don't have a lot of understanding about sort of the communication lower bound for this kind of problems. So this is actually the next thing we want to look at is this price of communication, right? How much communication do we have to pay if I want to achieve this linear speedup? In fact, if I want to achieve any speedup for this kind of regimes. So we have this paper that established this communication lower bound. So essentially, so I'm now showing you a lot of the details, but essentially we are analyzing kind of family of federated Q-learning algorithms with some kind of natural intermittent communication protocols. So very similar to the sort of paradigm I showed in the previous slide. You let the agents do some local communication, you then allow them to communicate, and then you do this sort of so on and so forth. So for this family of algorithms, regardless of your choice of your synchronization schedule. So you don't have to make the synchronization schedule to be periodic at all. You can have some design flexibilities there. But the number of communication rounds you have to make is at least on the order of the effective horizon in order for you to achieve any sort of speedup in your sample complexity with respect to the number of agents. Again, the interesting thing here is this is not just about linear speedup, right? You can be a little bit pessimistic by saying, oh, I'm very happy if I can just get maybe some sublinear speedup with the hope that you can reduce your communication cost. That is not going to happen in terms of this price you will have to pay for long horizon problems, as long as you are hoping for any speedup. Okay. So the result here also is shown in terms of communication rounds, but for the information series in the room, you can also get a result in this similar style by thinking about measuring communication cost in terms of communication bits, and then you get a similar kind of lower bounds. So to the best of our knowledge, this is sort of the first communication complexity analysis for this kind of federated RL algorithm that shows actually you do have a communication barrier. I should also say that, in fact, this is kind of unique when you look at a Q-learning type of algorithms where you have this nonlinearity in the Bellman's optimality operator. Earlier work, when people look at, for example, federated temporal difference learning algorithm, TD algorithms, because the policy evaluation operator is actually linear, there you can actually get a linear speedup even with a single shot of communication. But that's not the case here for the Q-learning setting because of the nonlinearity, and then we have the sort of barrier introduced by in this kind of long horizon problems. So let me maybe also mention briefly about the key idea we have in the proof. So roughly speaking, when you measure the errors in your Q function estimates, you can kind of break things down in terms of this bias variance trade-off, right? The nice thing with the variance is that it always exhibit linear speedup when you average things from different agents. So very nicely, the variance will enjoy linear speedup. But what happens with the bias is that as you start to do more local computation and makes the communication, sort of the gap between communication runs longer, your bias will actually increase. And the increase is sort of proportional to the number of local rounds you are doing. And when you do an averaging round towards the end, the bias kind of shrink a little, so it has a little bit of compensation, but the shrinking is actually not large enough, so it will not really compensate enough for the bias increase. So roughly, the figure look like, yes, so the bias will be actually accumulating over the federated learning regimes, and as long as, so as long as the bias actually dominates the variance, then you will not going to be able to get any collaboration gain, because the bias actually is sort of independent with the number of agents you have. So that's sort of the high-level idea. And in fact, the analysis we do here heavily leverage the analysis we have in this lower bound analysis for the single-agent Q-learning setting. So you get a sort of a similar kind of long horizon barrier in both cases. Okay. All right. So now with the lower bound in place, now we have a good understanding of both the statistical sort of optimality, what kind of the best statistical sample complexity we can have, and what is the best communication complexity we can have. So naturally, the question is, can you actually design an algorithm that achieves both? So in the paper, we actually have an algorithm that sort of leverages variance reduction and sort of communication compression to get sort of algorithm that achieves both the best sample complexity and the both the communication complexity. So for the sake of time, I will not talk about the algorithm here. It's indeed actually a little bit more complicated than sort of this natural variance we show here. All right, so let me now maybe move into the third part, which will be looking at sort of the heterogeneity aspects in designing federated Q-learning algorithms. With that, I want to actually move to a little bit more practical setting of Q-learning, which is in this kind of asynchronous setting, where you try to learn the optimal Q function by using data collected from some behavior policy. So let me maybe tell you a little bit what this algorithm looks like. So imagine that you have some agent that is taking actions according to some behavior policy, which is not necessarily the optimal policy. Then you're still going to use this kind of stochastic approximation approach for solving the Bellman's optimality equation. But now at every time, at every instance, you only see one transition tuple. So you're only going to update one entry in your Q table for the Q function. And the update is very similar to before, right? You just take this convex combination of the previous Q function in that entry with this sample version of it using the transition you see on the trajectory. So if you think about this as hopping around the Q table to do update, right? This is essentially very similar to some kind of coordinate descent update algorithm over the Q table. And if you have different behavior policies, you will be hopping along different trajectories, right? So that precisely leads to this kind of heterogeneous setting we want to study, is that now going back to this picture, right, we've been showing you, instead of assuming every agent has their own simulator that can just access all the state action pairs, these agents now can have their own behavior policies, right? And they may be exploring or visiting different part of the state action space. But the goal is still to learn the optimal policy. So the hope is that, is it still possible to maybe leverage this kind of heterogeneous data collected by different agents while accelerating learning, right? So that's the high-level idea. And also, we actually also want to get some sort of collaboration benefit, right? Now, back in the earlier part, if you actually just do single agent IO, then theory tells you actually have to have every agent visit the entire state action space. That's a pretty strong requirement, right? But on the other end, if I have multiple agents, maybe the best collaboration scenario should be I can sort of ask them to, maybe they can each responsible for a certain part of the state action space, right? So maybe they have different coverage over the state action space. Maybe none of them are covering the entire state action space, but maybe collectively they are covering the entire state action space, and that's already good enough. So that's sort of the idea, right? So can we actually show that this kind of collaborative coverage will be enough for the federated Q-learning algorithm? It turns out that this would be possible, but before I show my result, let me introduce a few key metrics to make things rigorous. As you can imagine, roughly speaking, at the end of the day, different behavior policies will induce different stationary distributions over the state action pairs, right, of the environment. So the quantity we care about, the first one is kind of on average how the state action space is being covered. So this is actually looking at the average visitations across all the agents and take the bottleneck entry, which is a minimum of this average distribution over the entire state action space. So this is an important quantity. Another quantity is to look at the heterogeneity of the local behavior policies. So what this is looking at is basically looking at the density ratio of each of the behavior policy with the average behavior policy. And you look at the worst case. Okay? So naturally, there are actually two extreme situations. In the first situation, if all the agents have the same behavior policy, then the heterogeneity parameter will just be 1. Right? And requiring, say, the mu average to be greater than 0 is the same as requiring every agent covers the entire state action space. On the other end, if I have, so this is again just for illustration purpose, but if I have each of the agents, let's say, only cover their own corner of the environment, then collectively, they will cover the whole thing. So in order to assume the average mu is greater than 0, I actually do not need to assume each of the agents covers the entire space. But then at the same time, the heterogeneity parameter can go as large as k, where k is the number of agents I have. Okay? So these two parameters are kind of competing a little bit with each other. So with this parameter in place, the sample complexity we show in this kind of heterogeneous case essentially is something like this. So I'm also ignoring a few of the things like the burying cost. So that's sort of before everything enters in this sort of nice stationary regime. But if you care about those, we have more complete version of these expressions in the paper. But let me try to interpret this as this result. So if, let's say, all the behavior policies are kind of nice and similar, so let's say in this case, let's say I can assume the heterogeneity parameter is just 1, then we do have the nice linear speedup here, right? So that's nice. And the analysis is actually quite evolved because of the Markovian trajectory. So you have to do some quite sophisticated leave one out type of arguments. But still, it's not completely satisfactory from an algorithmic perspective because, as I mentioned, perhaps the nice case I want to have is the heterogeneous case, right? When this heterogeneity parameter is close to being k, so that they can have this kind of collaborative coverage. But in that case, if this is almost like k, it will cancel your linear speedup on the denominator. So at the end of the day, we're not seeing any collaboration benefits, right? We're not getting linear speedup. So this gives a sort of question about, can we actually do better than this, right? And if so, how can we do better than this? So if you think about what we have done a little bit, maybe not very well, very nicely, is that when we are doing our averaging, right? If you have very heterogeneous data over different agents, then if you think about maybe for some particular part of the environment, some agent should have higher says because this agent visits this entry a lot. But maybe some of the other agents shouldn't have a lot of say to that particular entry because these other agents never really visit this state action pair. So intuitively, we shouldn't be doing the equal averaging, right? We should be assigning higher weights to agents that has better ideas about those particular part of the environment. So intuitively, what you should be doing is some kind of importance averaging. So the formula we use in the paper is something a little bit complicated like this, but essentially, you are going to assign higher weights to agents that visit those state action pairs more often. And the weights you use will be informed by by the visitation counts, essentially, some sort of counter, and using sort of the knowledge of your Q-learning update rules. Right, so that's sort of the high-level idea, is that you should be doing something like importance averaging in the heterogeneous setting rather than doing equal averaging. All right. So if you do this, you actually can get rid of the dependency with a C heterogeneity parameter on the numerator. And in fact, this is kind of a clear result in the sense it almost matches the sample complexity you will get if you just collect all the local data to the central server and let it to do its updates. Right? So this almost matches the sample complexity you will want to achieve in a centralized setting for this problem. And you can actually get similar results for offline RL, where you incorporate, say, the pessimism in the update. So put things together on a picture. We show that if you do equal averaging, you do still get sort of collaborative coverage benefit, but things the sample complex can be much worse so that you don't really have linear speedup. But if you design your importance averaging collaboratively, then you can actually always kind of realize the benefit of collaboration and match the sample complexity you can achieve sort of in the sort of centralized regime. Yeah.
So intuitively, why do we get a linear speedup? So in the regime when C hat is capital K, everyone's just seeing their disjoint parts of the table. Like how we are not really averaging the data I see from different clients. So how am I benefiting from?
But so in that case, you are getting benefit in the sense of the coverage. So that you only require mu average to be greater than 0, rather than each of the visitation behavior policy to have strictly to have a strictly bounded away from 0 for the entry.
So still some sort of average.
Yeah. So yes, exactly. So in the single agent setting, essentially the sample compact will be having this mu b on the bottom. So if you do it for each of the agent, you will require each of the agent cover the entire space. But in this case, you still only just require the mu average to be above 0. So you still have a little bit of collaboration gain, but you may not be getting a linear speedup. Yeah, great question. All right. Yes, I think I'm probably getting to the end of my talk. Yeah, so this is sort of the mental picture I want to show to everyone, is that I think there's an interesting synergy between doing statistical machine learning and reinforcement learning, particularly in this kind of federated setting, to think about how we can actually enable the collaboration of multiple agents for this kind of RL problems, even under data heterogeneity. So with this, I will conclude my talk. And these are some of the related papers. And if you're interested, you can find them on my homepage. Thank you so much for your attention. Happy to answer any questions you have. Okay. Yeah, I think we have probably some time for questions.
Someone have any questions? I have one more
Okay,
question for
sure.
you. So, so far the heterogeneity is only in some sense the visiting.
Yeah.
If everyone sees related but slightly dissimilar MDP, do you have intuition? Like what can we get?
Yeah, that's a great question. We are actually also looking at some of this type of problems. And I believe actually one that maybe Naveed will be giving, they have a paper also looking at where you have kind of a personalized setting if you have different MDPs. I think that's a very rich problem space because when you define the MDP, you have both the transition kernel and the reward functions. And you could have, say, all of them have the same transition kernel but different reward function. Or they have, like you said, they have maybe a little bit different of the transition kernels, but maybe they have some shared low-dimensional latent representation. So yeah, I think all those are very interesting problems. There is some of the existing literature for some of these problems, but definitely I think it's still a lot of open problems. Yeah, the algorithm will probably need some changes as well.
Are the number of samples like for each class the same?
Yeah, so in this case, we're assuming it's perfectly synchronized. So everyone does tau round, and every round they just